Hello, everyone. I hope you can hear me. Just let me know. Can you hear me? No. Hello, can you hear me?
Yes.
Oh, okay, thank you. Okay, so I guess we can continue our previous lesson. I will share my screen. Okay. Can you see my screen? Okay,
Yes.
thank you. So, mhm, okay. So we stopped at the neural networks part. So I'll resume it, only neural networks from previous research, and then we will go through another data set and another research. So first, what are neural networks? Neural networks are one tool, just like the other models we use, like linear regression, random forest, support vector machine, etc. But for neural networks, we have some neurons, as it is said in the name neural networks, and also we have some layers. So neural networks are a powerful tool for classification tasks, and also we can use them for regression. They have layers of interconnected nodes. So we have neurons called nodes, and we can model all the patterns in data with them. We have multiple types of neural networks. Here we will use a feed-forward neural network. So you will see how we can do it. About key concepts, we have layers, as I said. So we have an input layer. It's the first layer. And here we have our input data. Data is input, and then we have the first layer. After we have hidden layers, maybe we can have one or multiple, and hidden layers are layers between the input and the output layers, and everything is doing in between. So all the work is done in hidden layers. And the last one is the output layer. So the output layer is the final layer, and there we got the result. So we have input layer, hidden layers in between, and the output layer where we have the final result. After, we have some activation functions, and very popular is this rectified linear unit. We have sigmoid, etc. And that's our nonlinear functions. We apply them to neurons outputs, and with them we introduce nonlinearity. With them, neural networks can learn complex patterns and do something with the data. About loss function, all the loss functions, as in previous research, measure the error between predicted and actual labels, and you will see all the loss functions. And we have backpropagation. Backpropagation is a method used for adjusting weights based on the error, helping the network learn. And you can read all this. You'll get this file. So we had our data set based on the marketing campaign. So we had all these parameters that were our inputs, all of this. And we had DF, that's our data frame. We had the marketing campaign Excel file. So we read that file and put it into DF, our data frame variable. And we used DF for everything in the previous work. But now we want to use neural networks. So we have to first scale our data. That's our first step to use neural networks. We first initialize our standard scalar. We use standard scalar. There are multiple of scalars that exist, but we use this, and we first initialized it. It was imported in the first row of that code where we imported all the libraries. So we can use standard scalar by its name. And it is used to standardize features by removing the mean and scaling to unit variance. So what's the point? We just scale our data to have a mean of 0 and a standard deviation of 1. And with that, we just initialize standard scalar. We then said that we want X-train standardized data to put it into this variable. So we used the scalar, our variable scalar, where we have our standard scalar, and we use the function fit transform. That's a function, a method that fits the scalar to the training data. So we have our X-train, that's our training data from our data set. And with fit transform, the mean and standard deviation are being calculated. So when we calculated the mean and standard deviation, we can fit our data to the scalar and put it into X-train STD. And there, the data is scaled with all this parameters. After, we use the function transform. So the transform method is used. Here we can also use fit transform, but we don't use it because we don't want to refit the scalar to the test set. So we just use fit transform. And with transform, mean and standard deviation is calculated from the training set to transform the test data here. And we just ensured with this that the test data is standardized in the same way as the training data, avoiding data leakage. So we just use transform. So we know that X-train standardized is the same, is standardized the same way as X-test standardized. And the last step here is to standardize the entire data set. X is the entire data set, and we just applied transform, our function transform, because we want it to also be the same way, transform the same way as xtest and xtrain. So we use only transform, not fit transform. And our set x is now scaled and put into variable x standardized. And now we have 3 variables with the standardized data. After we standardize our data, we can do something with it. And we created one neural network. Here, we used MLP classifier. That's one type of neural network. And we imported it also in the first row of this code. So we just manually put some parameters and their values. With MLP classifier, the MLP classifier is initialized. MLP is, as this name says, multi-layer perceptron type of neural network, and it's classifier. It's used for classifying the data. And here we have parameters like hidden layer sizes. We have 3 hidden layers with 8, 8, and 8 neurons. After, for activation function, as I said, real rectified linear unit is very popular and commonly used. So we used it here also. And this activation function introduces non-linearity. Then we use solver. It's Atom, and Atom is a popular optimizer, so we just use Atom when we don't know what to use. So you can use Atom, and you can Google another ones to try. And all of these solvers, optimizers, adapt linear learning rates during training. And the last parameter is max iter. That's the maximum number of iterations. So the number of the maximum number of iterations the model will run during training. And when we reach that number, our model will stop training and the work is done. The last step here is to fit the model. So we use the fit method to train the neural network model on the provided data, xtrain standardized and epsilon train. So we use training features that are in this variable and use our output features that are in epsilon train, and we just fit the data using the fit function. So that's the process for learning and training the neural network model. Then, when we don't want to manually input some parameters and we don't know what to use or don't know which parameters are can effectively be used in all of this work, we can use something called grid search for neural networks. So we just defined all the parameters with their hyperparameters, solver, max iterations, alpha, hidden layer sizes, and their values. That's some type of grid, and put it into variable neural network parameters. And then we performed grid search. Here's the function grid search that was previously imported. And we used MLP classifier, that's our classifier, our neural network. NN parameters and accuracy for scoring. We want to see the accuracy of this training and of the results. And we fit this parameters used there with grid search to xtrain standardized and epsilon train. And when we use grid search, we will get the results. That's our best score and best parameters. And then we know which parameters work the best for us and we can use them after. So when we printed the best score and the best parameters found, we initialized MLP classifier with the best parameters. That's our best parameters here. Number of optimal parameters dot best parameters will return the best parameters of our model from this list. And after we just fit our model with the standardized training data. So now we have our model that works the best for us. For the prediction, we just use a function predict with excess standardized data, and in epsilon we got the predicted data, our predictions, and then we just print our results. So that's just a line of code, results on the test sets here. We call the function classification report with our epsilon test predicted, and we printed the confusion matrix with the function call confusion matrix with our epsilon test and epsilon test prediction. Sorry. And the matrix results that is in CLF report. So here we can see our best score. It's 0.888, etc. Our best parameters are from this list, but they're sorted. So now for the best parameters, we have activation, that is rectified linear unit. Alpha is 100. So we have multiple choice, but this code decided that the best for alpha is 100. For hidden layer sizes, we have 3 here. There we had multiple choice, so the best value was 3. Then for max iterations, it is 500, random state 0, and solver LBFGS. For the results, here we can see confusion matrix, accuracy, and the results. And for the activation, our best parameter, rectified linear unit activation function, is used, and it is commonly used. So it introduced nonlinearity and speed up training. The alpha parameter is 100, and it is a regularization parameter that controls the model's complexity. And if it's larger, it's preventing overfitting. About hidden layer sizes, we can have as many as we want, but we here have only one hidden layer. So we have an input layer, one hidden layer, and an output layer. That's 3 layers, and only one hidden with 3 neurons. So we can see that we have 3 neurons in this hidden layer, and our architecture is of course simple because we have only one hidden, only one input, and only one output. About max iterations, our model will run for up to 500 iterations. For random states, we just ensured that we will start every time with the same parts of the data set. That's just a random seed. And for solver, we used LBFGS solver, and it is efficient for smaller data sets. Our data set is not that big, so that works good for us. About the results, as in the previous lecture, here we have confusion matrix. This value here is true negatives. Class 0 correctly predicted as 0. After this number here is false positives, it means class 0 incorrectly predicted as 1. This number here is false negatives, and that means class 1 incorrectly predicted as 0. And this number here is 24, and it is true positive. Class 1 correctly predicted as 1. About the accuracy, we got this number here. So that means 88.96% is our accuracy. Our model correctly predicted for that percent of the test set. So the accuracy is good. And here you can see the detailed metrics. You have all these numbers explained here, so you can read it and maybe understand it better. But we can see, as in previous results, like the results for random forest, support vector machine, we got all these results that are slightly worse, I think, but we got the same results. The model performs well for class 0, but it struggles with class 1. That's the same result as in a previous test. So we can see lower precision for class 1. And you can see it here. For class 0 is 0.9, but for class 1 is 0.6. Here we have 0.3, 0.4, so it's low. And the model is suitable for tasks where predicting class 0 is more important because we have better results for this class 0. And this is all about neural networks. Of course, you can try to create different types of neural networks. You can try to use different architectures, maybe different hidden layers, maybe more hidden layers, different sizes, or you can use grid search and try with grid search. So everything here you can try and see what works for you the best. After the marketing campaign data set, I will show you another one. Here we have the Boston housing data set. And as in previous research, I had the Excel data. If you want to just write housing CSV, you have to put this file into the same folder as Boston housing dataset. But if you have this file somewhere in your computer, you just write the whole path here. So you will have maybe user desktop housing CSV. But for me, it works well with this because I have housing file in the same folder as Boston housing dataset. I will send you everything after this lesson. So about the Boston housing data set, it's open source. You can see this data set at Kaggle called Boston House Prices data set. This is linked. So if you go to this link, you will get to the Kaggle site, kaggle.com, and here you can see all about the data, and you can download the data set housing CSV. Here you can download it and use in our research, but I will send you this data set, of course. Our goal is to analyze these features to predict housing prices in Boston, and we use machine learning techniques to develop models that are capable of accurately estimating the prices of houses in the Boston area. And this prediction can be valuable for maybe real estate professionals, maybe homeowners, maybe buyers, but we will try to do this the best way. About the data set, I said it's from Kaggle, and the data set is collected in 1968 by these people here, and they wanted to predict real estate prices with all these, using all these parameters. So we have some CSV file, and there we have columns. That's our parameters here. The first one is this here, CRIM, the crime rate per person in the town. After we have set 10, the percentage of residential land in the town with large lots. Indus is the percentage of land used for non-retail businesses in the town. This chess is whether the property is near the Charles River. 1 is for yes, 0 is for no. NOx is the air pollution level. RM is the average number of rooms in each house, number of rooms, so rooms. H is the percentage of houses that were built before 1940 and um, still have people in the houses, still are used. This is the distance from the town to major employment centers in Boston, weighted for convenience. Red is a number representing how easily the town can access major roads and highways. Tax is the property tax rate per 10,000 of property value. After we have PTRAT IO, the number of students per teacher in the town school. B is some measure, and here we can see how they measured that proportion of the Black population in the town. L stat is the percentage of people in the town with lower economic status, and ADV is the median mill value of houses in the town measured in thousands of dollars. So we used all of these parameters and then predicted the price. So we have factors that are prices, we have crime, pollution, and all the parameters for accessibility. The first step is, of course, to import the libraries. We use pandas for data manipulation, NumPy for numerical computations. We use matplotlib pyplot as an alias PLT. This is NP, this is PD. That are all the aliases. We can use them by this name and with this name. So you can choose, but it's more efficient to just write NP or PLT. After we used Seaborn for data visualization, standard scaler for scaling, train test split and randomized search CV for splitting data and hyperparameter tuning, linear regression model, random forest, XGBoost, cross-val score, mean absolute error, R2 score, mean absolute percentage error for loss, evaluation metrics. We used polynomial features, Ridge, RFE, pipeline, and grid search. You will see all these libraries in the next code. After we imported all of these libraries, I can run the code and I can use all of them in the next line. The second step is to import the data. Our file is housing CSV with all these columns and rows with the data about houses in Boston and their price. So we just wanted to read. At the previous lesson, we read Excel file. Here we have CSV files, so we just read CSV, the name of the CSV file, and delimiter how the data is delimited. And we had no header, so we just write this and run our code. With dfhead, we can see first few rows. The default is 5. You can type some number here and you can display another number of the columns and rows. And that's our data. Here we don't have names for columns, so we have to manually type the names. Column names are the names of our parameters I listed here. So I just wrote them all in this list. I have criminal rate, Satin, Indus, chess, etc. I put them into list and initialize the column names. And after I set the columns name, so with dataframe.columns is equal to column names, I set the column names for my dataset df. And with dfhead, when I run this, I can see that now I have all the names for my columns here that were only the numbers. Now I have names. We can also overview our data and see how it looks like. So with df.info, we can display information about our data frame. We have data types, and we have the number of non-null variables, non-null instances. And we can see that the number is the same for them all. So I guess we don't have any missing data or any duplicates, but we will see. With df.d types, we can display the data types of each column in the data set. So we have floats, we have integers, just numerical types of data. Then we checked how many null variables we have, missing values. So we first call the function isNatt to check whether the value is missing or it isn't. And then we summed them all. We summed the number of missing values in each column. So we can see that there is no missing values here. So we don't have to insert something or delete something. It's okay. After, we checked duplicates, and with duplicated function dot sum after it, we can just sum the number of duplicated rows, and the number is 0, so we don't have any duplicates and we don't have to remove anything. Our data set is fine. After, we get the number of unique values in each column with n unique number of unique values, and we can see the number of unique values. For crime, it's 504. For chess, we have only 2. For red, we have 9, etc. That's the number of unique values. Then we described our data set so we can see the descriptive statistics: count, mean, standard, minimum, first, second, and third quartile, and maximum value. In the last lesson, I told you everything about this value, so I think you all know what that means. And something interesting happened here. For set n, this column here, we can see that we have 0 for minimum, 0 for 25% of data. So first quartile, 50% and 50%. So for this tree, we have 0. And also for chess, we can see the same. Minimum is 0, and first and second quartile, and here the third quartile is 0. So these values are categorical, and maybe we don't have to use them. Maybe they're not useful for this research, so we will think about it. And also, we saw for the medium value, this here, we can see the value 15, and that's our maximum value. So any value above this value may not be helpful for predicting this price. And we will see this through the examples. With np.shape, we can see our dimensions, rows and columns. So we have 506 rows and 14 columns. Then, as we can see in this table for chess, where we had 0 for all of these rows, and we thought about it and said, okay, chess is not that important to me. We can drop this column. So we removed chess column from the data set because it is categorical and don't have such an impact for our target variable, and the target variable is the price. After we dropped, I guess I ran this, okay. We removed it and we said, okay, I just want to see the first row with df.head. When you specify the number, you can see that number of rows. And we can see here that we don't have the chess column listed because we removed it. After this medium value, MEDV, means nothing to us. So it's better to rename it to price. So it's more understandable. And we just used rename function with our data frame. We said, I want my column MEDV to be called price. And in place true to have the changes into this data frame. So with this line of code, we just renamed the column. And when we run df.head, we can see that now we have the column called price. That's our target variable. Then, as in previous lesson, we can see and explore our data. And at first we used heat map. Here we created a figure for the heat map with this size. You can choose your size, what works best for you. And we just plot a heat map. We call the function core to have all the correlations between our variables. And with this library sns.heatmap, we can have our table. And now we can see all the correlations and all the relationships between variables. The one is highly correlated, 0 is low. So we have, maybe I can see here. Maybe this number here, crime, is highly correlated with red here because the number is not that high, but for this standards here it's high. But you can see some, oh, this one here, price with RM is highly correlated. Maybe this here. This number here is also okay, but we have some variables that are not correlated, like B and Z10. That number is very low, and maybe Z10 and crime, etc. So you can just analyze this heat map. Also, we plot the histogram. We used price column. So we just wanted to see our prices and their count. For feature distribution, we used histplot to just plot histograms of all the columns, all the parameters, and we can see crime, Z10, Indus, NOx, etc. And here you can see how to do it. You can change the numbers and you can change the number of subplots, etc. But with this code, you can create the figures like I created. And here you can see how the data looks. Look. And from this picture, for crime, we can see that this data is not normally distributed. Also, we can see it for Z10, only this is not distributed normally. And also we can see this for B here. This line is not normal. And maybe we can remove them also. So maybe they can lead us to less accuracy, but we will see. We also used tight layout to adjust the layout to prevent overlap of titles and labels. So we can have them clean here. And here you can see all the histograms for each columns in the data set, and they're zoomed so you can have a clear view, and you can see all the data here. After, we use joint plot to visualize relationship between crime and price, and you can see as crime is bigger, the price is lower. So we have that relationship here. And our X column is crime, our epsilon column is price, our data is our data frame DF, and we used reg for the type of joint plot, and we just this regression line, I mean for kind, and we just saw the relationship between our parameters here. The next plot is box plot. We used box plot between all this for all these columns, and with box plot we can see the outliers clearly, and we will use box plot in the next minutes to show the outliers. Here we just created a figure with this size here. We created a box plot with our data. We set the title called box plots of all columns, and we said I want this all these names to be rotated with 45 degrees to have a clear look, and just show my plot, display my box plot, and we can see the box plot for all these parameters. Then we use box plot for only LSTAT, and it's used in the same way. We plot our figure with this size. We said I want only to box plot LSTAT, only one variable. We set the title box plot of the LSTAT column, rotated the name here. We don't have to do this. You can delete this and display the plot. So now we can see our box plot for LSTAT column, and all these points are actually our outliers, some data that is beyond our analysis, I guess, but we'll see this later. And for scatter plot, we use scatter plot for number of rooms, so rooms, and price. And that's the dependency of property price on the number of rooms. And it's used in this way. Plot a figure, then plot scatter plot with for the x for the x we use rooms, epsilon is price, title is this here. We said font size is 20. You can use your size. Just labels for x, that's our label here, labeled here for epsilon, and showed our plot. So we can see the dependency. Maybe for this point here, we have 9 rooms, and the price is between 20 and 13. Okay. After, we used a scatter plot to show the dependency of property price on the crime rate in the area. So we have crime rate for x and price for epsilon, and it's used in the same way, just to see this dependency. Then we use the dependency of property price on the proportion of residential land in the area, that's Zn. Zn is our proportion of residential land. For epsilon is price, and we can see the dependency. We also used this plot for Indus, proportion of non-retail business acres, and price. And that's the dependency. We have multiple more, so I guess now we can have 15 minutes to rest and see you at 7. Thank you. Hello again. I hope you can hear me now, but let me know with just one yes in the text, in the chat. Can you hear me?
Yes.
Yes, we can.
Okay. So we can continue. We use scatter plot to show the dependency of property price here and concentration of nitric oxide in the area. That's our NOx value. Then we use also scatter plot, but here we use it to show the dependency of property price on the age proportion of the units built before 1940. And you can see it here. The code is the same. We just choose different variables, different parameters, and the title and labels are different, but the code is the same. We then use scatter plot to show the dependency of property price on this. That's weighted distances to employment centers. So we can see the dependency here. Then we use scatter plot to show the dependency of property price on the index of accessibility to highways. So that's our parameter RAD. Then we used scatter plot to show the dependency of property price on the full value property tax rate. That's our tax parameter. And we can see the dependency on this plot. After we use scatter to show the dependency between price and B, proportion of blacks. Then we have the dependency of price on percentage of lower status population. That's LSTAT variable, and that's it for the scatter plots. Then we use pair plot to just visualize pairwise relationships in the data set. And we showed and displayed all the plots, and all the plots are here. So each relationship between our columns, our parameters are there, and you can see them all. You can also save this file. You can expand the image, click here and expand, and you can copy to clipboard and then paste. That's the three functionalities here. Okay. And when we plotted all the graphs and saw each relationship we want to see, we can start the pre-processing. And first, as in previous example, we want to see the outliers and we want to remove them. But here we used box plots to just see all these points that are too high or too low, that are not in this particular point part. And we used this variables, this columns for the outlier plot, crime, SAT10, indus, etc. We looped over the list of these attributes and draw a box plot for each column. And then we wrote box plot of, so box plot for first, for second, for third variable, etc. And then we just showed our plots. This box plot for crime, and you can see all these points here that are our outliers. For SAT10, you can see them here. For Indus, it's okay. You don't have any missing points. here and here are for RM. For age, we can't see anything. For this, we have these points here. For RAD is okay. For tax is okay. For PT ratio, we have this on the left. For B, we have a lot of outliers, so we will remove them. And for LSTAT, you have these values here. So on the previous lecture, we used something called interquartile range, IQR, and we will use it also today. It's popular and it's not, it is simple, so you don't have to think a lot about this methods. And as I told you in the last lecture, these are the steps for outlier detection and removal. We first have to find the first quartile, that's the 25% of data below the value. After, we have to find the third quartile, 75%. We calculate interquartile range, that's Q3 minus Q1. And we define normal data range. Lower limit is Q1, the first quartile, minus 1.5 multiplied by our interquartile range. And for the upper limit, it's Q3 plus this 1.5 multiplied with IQR, just to say, okay, I want some values on the left and on the right, but in this range. They're okay. Each point that is upper or lower these two values is an outlier, and I want to remove it. So here is the method of detecting and removing outliers. We defined IQR method, and it takes the data frame, it takes the number, and it takes all the features we want to use. And DF is data frame, input data set, N is the number, threshold for how many outliers needs to have to be considered an outlier. Features, that's a list of column names, that's our columns, our parameters, and it returns multiple outliers. You can see that's the list of all of our outliers. So we create a list to hold indices of outliers from all columns. We loop over the features columns in this dataset with this for loop. So we go through each column in the features list. We calculate first Q1, that's our first quartile, interquartile range, which is the 25th percentile of the data, as I told you. We calculate the third quartile, Q3, that's the 75th percentile of the data. And after we, as you can see, the third step, we just say IQR is Q3 minus Q1. So with this line, we can calculate interquartile range. We defined outlier step, that's 0.5 multiplied with this value. You can see it here. Okay, then we identify all the indices where the data is below the lower bound or above the upper bound, so to the left or to the right, and that's here. And we append this outlier indices to the main outlier list with extend function. Then we count how many times each index appears in the outlier list, identified indices that have more than n outliers, and calculate and print the total number of outliers below the lower bound, so to the left, and above the upper bound, so to the right, and just printed that number and return the multiple outliers. And that's our numerical columns list here. We use IQR method and send our parameters. So we send our data frame, we send one for the n, the number, and we send numeric columns. That's our numerical columns here, and just performed the iquar method. The result is in outlier iquar. And when we do this, we can drop all these points with drop function. We just send our variable outliers iquar and say, okay, I want to drop all these points, all these values, and put it into data frame 1. So now we have data frame 1 without all these outliers. Okay. I guess I can run all. I don't know which code I have run. Okay. We printed now our data frame shape without the outliers, and this is with and this is without. So we can see that we removed about 50 values. When we prepared our data set, we can create our list for creating models. So now we prepared X and Y. Our target variable is price. So we dropped our price and all the other columns are X. So price is our target and we created epsilon, that's just the price column. And now we have X, and with x.head we can see what is in our X. It's all the columns but without the price. For epsilon, we have only price. And we can see the first 5 rows for both the X and epsilon. And then when we created our X and epsilon, we can do the feature scaling. We used standard scaler and we transformed all the data to have a mean of 0 and standard deviation of 1. That's what the standard scaler do. And also you can have multiple scalars and you can Google and learn all about it. The standard scaler works best for our problem here. And this scaling is done to each column in our data set. Okay. Just a sec. Okay. We created this function standard scaler. So in features variable, we selected all the columns that need to be scaled. That's our columns call name, and we send them here. So all these columns are the columns that we want to be scaled. And it's here. After we created an instance of standard scaler, and this standard scaler will calculate mean and standard deviation of the data for scaling, and then with fit, the model learns the parameters of the data, mean and standard deviation, and then when we do all this, we can put it into our scaler and scale the data with scalar.transform. So with transform function, we can scale the features by subtracting the mean and dividing by the standard deviation. We send our features values and put it into features. After that, we can replace all the columns. So all the columns in our data frame, df of call names with features, and we just updated the columns in the data frame with the scaled values. So now in our initial data set, data frame, we have our new scaled columns. We return the data set, and now when we call the function centered scalar with our x and with our column names, we have the scale data in x scaled, and we can use it for future research. When we do this, we can apply something called cross-validation. Cross-validation is a technique that is used in machine learning to assess the performance and generalization of a model. And what's the point? We we do the partitioning of our data set, so we can have multiple subsets for training and testing. So we evaluate our model on different subsets of data. The point is to have multiple training and testing parts of our data set, so we can do something with it and just test and try. Here we use cross-validation to evaluate the performance of a linear regression model. And we just want to make sure that our model performance is consistent across different splits of the data. And here we imported linear regression model. We used it in the previous research, and cross-val score, that's for performing cross-validation. So we have to import it because it's not imported in the first segment of code. And also you can maybe copy this and paste into first segment and delete from there. That's not a problem. When we imported it, we can create our linear regression model. You know to do this. You just type linear regression by its name because it's imported here, and put it into some variable called linear regression LR. And this initializes a linear regression model that will learn a relationship between the input x and the target epsilon. Then we perform our cross-validation. We use cross-val score, and with cross-val score, we just perform cross-validation. Here is the number of something that is called folds. We have Stevie is 5, and we split with, so this number means I can split my data set into 5 folds, into K folds. Here is 5. And after we say that we want 5 folds, we train our model on this number minus 1 folds and test on the remaining 1 fold. So here, when we have 5 folds, we have 4 folds for training and 1 fold, so 1 part, the remaining parts for testing. Xscaled is our scaled input features. We got that here. And LR is our linear regression model. So we used the method cross-val score, sent all these parameters, and the result is in score. With this line of code, with print, we just print our validation score. So our validation score is in score variable, and each fold score shows how well the model performed on that fold's test set. You can see it here. And we print the average score, and the average score is the mean score, and it gives an overall performance measure of the models across all 5 folds. And here is the validation score for each fold. So for first fold, second, third, fourth, fifth, and that's the average score. The average score is not that good. You have 0.2, that means it's not that good. 1 is the best, 0 is the worst. So you can have a clear measure that doesn't work doesn't work well, but it's relatively good for first, second, and third fold. But you have here minus, so some negative score. That means the model performs worse than simply predicting the mean value of the target variable for those folds. And this low score means something isn't good. A low average score, as I said, indicates that the model is struggling to generalize well across the data set. So we have to do something else and change something, maybe use some different model, maybe got different data, etc. After we train, test, and split our data, so we had all these variables: x train, x test, epsilon train, epsilon test, with the train test split method. X is our input parameters, epsilon is our target, our test size is 13% in this case, and the random state is some random number, 42. So we have training features, we have test features, we have training targets, we have test target. We have test size, that's proportion of the data set to include to the test split. So 0.3 is included to test, and some seeds random number generator to use for reproducibility. And we printed the shapes of the training and test sets. The training data shape is this here. So we have this number of rows and 12 columns. And for training, we have this number of rows and only one column, of course, because we have one target variable. For tests, we have this number here of rows, this number here of columns, and for tests, this here. After, we have to use scalar to scale our data, and we just send our train and xtrain and call names to scale, and xtest and call names to test, and we put the scaled variables into the xtrain and xtest. We prepared our lists, and now we can use some models. First, we use linear regression, the simplest model. It's used for regression because we have price as target variable, and that's the regression problem. We don't have classes, we don't have class A, class B, etc. We have some continuous variable, we have price, and with this we have to use some regression models. The first is linear regression, and we created one linear regression model, and then we just fit it with xtrain and epsilon train. And when we trained our model, we created predictions with the function predict. We sent xtest, and we got all our predictions listed in epsilon pred. So the value of epsilon intercept is put here. Okay. We visualize the model performance with this graph. We created the figure for this plot. We used scatter-plot, and we sent epsilon test and epsilon pred, epsilon predicted, so we can see a measure of how well our model performed, because we can see all our test epsilon and predicted values and just see if they're the same. And we added a regression line here to show the relationship and print the labels: actual prices, predicted prices, and the title. We calculated our errors. The first is mean absolute error. The second is mean squared error. R2 score is third, and mean absolute percentage error. And when we run this, we can see that the mean absolute error is this here, mean squared, r squared, and MAPE is about 14.9%. So it is average. It is okay, not the perfect one, but is okay. And we decided to try another model. Maybe we can get better results. So we chose random forest. It's a popular one and maybe is good for our task. So random forest, we created our random forest regressor with the random forest regressor object here, class and object. We initialized it and we say, I want this number of estimators, I want this random state. We chose the parameters manually and we started training with fit function. So now we have our model here. That's the same line. Okay, we don't need this here. We predicted the values here just with calling the function predict. And now we can get all the parameters that we use with random forest. I printed them here and we can see that we used that the bootstrap is true, the alpha is 0, that's our criteria, max depth, max features, and what is bootstrap? That parameter controls whether bootstrap sampling is used when building trees. If we say true, each tree will be trained on the random sample. If we say don't, it won't be trained on the random sample. For the alpha, if it's positive, here is not, but if it is, it helps reduce the complexity of the trees by removing nodes that contribute little to the model's performance. We don't want it here, so it's 0. About the criteria, it defines the functions used to evaluate the quality of a split during the tree building process, and our default for regression is squared error, so we used the squared error. About the max depth, it's the maximum depth of each tree, and we didn't set this value. We said it's none because the trees will grow until each leaf contains fewer than the minimum number of samples specified by min sample split. And we have min sample split here. About the max features, this controls the number of features to consider when splitting a node, and it can be an integer, a float, a string, and we here used only one, a float, 1.0. And by limiting the number of features considered, random forest reduce the risk of overfitting and help improve the model's generalization. Max leaf nodes, this parameter specifies the maximum number of leaf nodes in the tree. Here we have none. And max samples, it's set to none, but it is the number of samples to draw from the data set for each tree. Min impurity decrease is 0, and it is required for a split to occur. And all this minimum samples leaf, split, etc. is for the trees. And estimators is an important one. It's the number of trees in the forest. And drops is none, etc. You can see and read all this if you don't know in particular what each parameter means. And when we did all this, we can plot and visualize our performance. Here we chose the size of a figure, scatter plots, epsilon test and epsilon pred to see the difference between our predictions and our test data. after we added a regression line and all the labels and text, and we can see that our results are good. We have actual prices, predicted prices, and for some prices, they're the same. Like this point here is the same, but we have some values that are not, maybe this here, actual prices here, but the predicted price is somewhere lower, and you can read all that from this graph. Then when we do this, we can fit random forest model to the training data. We have training data here, epsilon, predict, and calculate another types of loss and measures. We use R2 score. That's a value between 0 and 1, and 1 is a perfect fit. So it's a measure of how well the model explains the variance of the target variable. We then chose to use adjusted R2, that's the formula, and we just want to print it and see this number. That's for the number of predictors in the model, preventing overfitting, so it's adjusted. It's adjusted R2 score, the previous score we used. Then we performed a cross-validation with cross-val score. We used it previously, and we just sent all the values here and got the result here. We wanted the mean value of our two scores for cross-validation, and with this we can just see if our performance is okay. And for this mean squared error is deprecated, I guess you can use root mean squared error in newer in latest versions of Python, but it can be used still, it works. So I use it as mean squared error, but you can type root mean squared error, I guess. Yeah, squared is deprecated and will be removed somewhere in the future. Use root mean squared error. So just type root here, but it works with this name also. And after we used all these functions, we can print the results, and 1 is the best, 0 is the worst, so we can have a clear measure with these values. 0.64 is okay, and adjusted is better, and for cross-validated is 0.7. That's some value that is okay for our research. And for this is the conclusion. So we use random forest regressor model, and we evaluated the performance of our models. We used 506 entries, so we have that much instances, that much rows, and we used 317 samples for training and 137 samples for testing. That's the percent we defined previously. And we, for training data, had 12 features, and the test data had the same number of features. That's our columns. The validation scores from 5-fold cross-validation were mixed, with values ranging from this number here. And this suggests that while the model performed well in some folds, it performed poorly in others. And somewhere we have negative R2 squared scores. So the average is indicating some moderate performance, but variability across the folds. Also, with these results here, we can see that mean absolute error is approximately mean squared error. Just it was yeah, mean squared error. I didn't print it. Yes, I print root mean squared error is this value here. Root is okay. And here you can read all the explanation. But from these numbers, you can just see, okay, 0 is the best. These values are close to 0 is the worst, 1 is the best. These values are close to 1. They're okay. I, of course, can have better results and I will find better solution, but they're generally okay. And after we use random forest, we have another one popular method called XGBoost. And here we implemented one XGBoost regressor model. Here is the number of boosting trees. So we had number of estimators 1000. Then the max depth of our tree is 7. The ATA is 0.1, learning rate. Subsample is a fraction of samples to use for each boosting round is this number here. And call sample is the fraction of features to use for each tree. We use this manually, but you can also use grid search as for random forest to find better solutions. We do the training with fit, xtrain, ytrain, and predicted our values with predict function, and we send the xtest list. We visualize our performance. So we have actual prices, predicted prices, we had the regression line, and we can see that works well. And after we calculated errors, we have R2 score, we have adjusted R2, we have cross-validation for our XGBoost model and root mean squared error. So we got all these results. I can see they're slightly better than random forest, but not the best, of course. 0 is the best, so maybe 0.9 will be some excellent score, but they're okay, and I can go with this. Here is all the explanation about this results. And the last one we can see is this recursive feature elimination. So we can eliminate some features recursively. It is a method used to select the most important features or attributes for building a machine learning model. And for you students, this is a simplified version. So what is this feature elimination? It stands for recursive feature elimination. It's a feature selection technique that helps identify which features are most useful for predicting the target variable in the dataset. This is important because sometimes not all features in the dataset contribute meaningfully to the model, so I just want to delete some features, and some of them might reduce the model's performance, so they're not good for our predictions, and I just want to eliminate them. How the RFE work? First step is to start with all features. Initially, we use all the available features in the dataset to build a model. After we evaluate feature importance, the algorithm measures the performance of the model, how well it predicts the target variable. Then we remove the least important feature. So the least important feature is being eliminated, and we rebuild the model with all other features. We use all the remaining features and it checks again the performance. Step 5 is to repeat the process, and we repeat the process. The process is continued until the desired number of features remain. And this why is it useful? Of course, we will optimize all the steps, and with good feature selection, we can have better results. And you can use this and try this feature elimination and see if you get any better results. So we initialize our FE object. Our estimator is random forest regressor, so we want to use random forest model, and this is the number of features to select. So that indicates that we want to retain only 60 most important features. All the others are being removed. We create random forest regressor model, and our third step is to create a pipeline object that contains this one here and random forest regressor model here. A pipeline allows us to combine multiple steps into one workflow. So with a pipeline, we can do multiple things at the same time. The first step is the feature selection using RFE. That's our object here. And the second step is training of the random forest regressor model. So we will do this here, S and M, you can see them here. We will do that at the same time. And this way, the pipeline ensures that feature selection is applied before training the model. We do the training, so we use the fit function, and after we put the predictions into epsilon spread, and here the model is making a prediction on our test data X test. We visualize the performance, and here we can see the regression line, and we can see the actual prices and predicted prices. And with number is everything better. So when we see all these numbers, we can see if the model is good or not. We calculated our squared score. We adjusted R2 score like in previous examples. We use cross validation score and mean squared error. So when we see the numbers, we can see that this time our model performs better and slightly different than previous ones. You can see the 0.82. That's excellent prediction, excellent accuracy. So you can see that this optimization, the recursive feature elimination, is very good, and you can try this when you have many features to just see which features work the best for our problem. And the last one, I guess, is the hyperparameter tuning using grid search CV. So with this, you can also get the best parameters, not the features, but parameters this time. So maybe your model will perform better when you just optimize all the hyperparameters. Okay. Hyperparameter tuning is crucial in machine learning, and it helps us to optimize performance of models. Grid search is a technique used for tuning the parameters, where a grid of hyperparameters is specified and the best combination is selected. For grid search CV, you can see how it works here. So we just define first steps of the pipeline. We create the pipeline with defined steps. We do the training. We do the prediction. We defined alpha values to be searched, our parameters. We created grid search CV object with RegPipe alpha parameters and a number of folds. And we do the fits, we do the training, predict all of this and print the best parameters. Here is the graph of the actual and predicted prices and calculation of everything. So with this, we got not that good as in previous result, but it is okay. So we can say that our model works the best with this optimization here and with random forest regressor. I will send you this file. You can read everything, try everything, and then if you have any question, you can send me a mail, because I guess we don't have any time now, but if you have some quick question, of course I will answer it. I will write you my mail again. So if you have anything to ask or some problem I can help you with, I am happy to help you or share something with you. If you don't have any question, I guess we are done for today. Do you have any question?
Oh, thank you.
No, thank you.
Oh, thank you. Okay, so I guess you all want to rest. This is a late term, so have a nice evening. I hope you learned something new. And if you have something to tell me, just send me an mail. Thank you very much.
Thank you for the lecture. Have a nice evening.
Thank you.
Thank you.